Okay, today I'm going to tackle the analysis of variance. And over the last couple of days I've been mentioning sum of squares, variance, standard deviation. And hopefully by this time you're quite happy with those concepts. Now just to introduce what we're trying to do with analysis of variance, I have a data set here. I measured seedling lengths in 6 cultivars. It doesn't show right to the bottom. I had 4 replicates, and there's my seedling length in millimeters. Right. Now the question that I'm essentially asking here, and I always hammer the fact you need to know what the question is. The question here is, do those cultivars differ from one another in terms of seedling growth? Now, the first thing that an analysis variance program does, and all the programs work on the same principle. The first thing an analysis of variance program does, it works out the total sum of squares. I did this manually just to show you what it's doing. So what it does is it works out the mean, and then it works out the sum of the squared deviations from the mean. Okay, so here I have a little formula. So it's the deviation of each one of those data points from the mean squared to get rid of the negative values. And when you add them all up together, you get this figure of 55,238, and that becomes your total sum of squares because it includes a variation in all the data. What it then does is it creates a matrix of your data. So you'd have the cultivars and you'll have your reps. And what it does is, based on the totals, it works out a new sum of squares. But it's a sum of squares just for the cultivar totals, not for the whole lot. And it comes up with a value, and because there were 6 cultivars, it divides the value by 6, and you'll see a value of 965 there, because this is the total of reps here, sorry. And you'll see that becomes your reps sum of squares. And it does the same for the cultivars, adds up all the totals, works out deviations from the mean, and it'll work out a cultivar sum of squares for you. Okay. Now basically so you've got the total sum of squares, you've got the cultivar sum of squares, you've got the rep sum of squares, and the difference between the total sum of squares and those becomes your error. And your error is simply unaccounted for variation. The next thing we do is we divide the sum of squares by the degrees of freedom, because that's what we need to do to get sort of the variance. And you end up with a cultivar variance, you end up with rep variance and error variance. Now the question is, do the cultivars differ, or is the variation due to cultivars significantly greater than the error? In other words, what we haven't measured. Can I say then with some degree of certainty that the variation due to cultivars differs from the variation due to error? So what the analysis of variance then does is it takes the ratio of, in this case, cultivars divided by error, and it works out an F value. And then depending on the degrees of freedom, you can look it up in an F table, but most of the programs will work it out for you anyway. It will then give you a probability value, which says I can say with a 95% probability that cultivars do differ and that they are a significant source of variation. And I can do the same for the reps. In this case, the F value is very small. The reps didn't differ significantly from one another. And that is the basic principle on which all analyses of variance work. So it's a very simple principle. You're just comparing your observed variance to error variance and the ratio. And all the different designs you get for analysis of variance are basically designed to maximize that effect, or if it's a randomized block, you also want that effect. I've marked them in green there, and to minimize the error effect. So whether you're doing a complete randomized design or randomized block design, factorial design, whatever design you're doing, okay? Lattice design, augmented designs, those were not some of the things that came out here the other day. It doesn't matter. The principle stays the same. The design is there to maximize your treatment effects and minimize your error effects. So that's as simple as it is. So that's why I've put that on, so that hopefully you can see where we're coming from when we look at the different designs.